We will now look at another historically very important harmonic oscillator, the simple pendulum. This consists of a string attached to a bob with some mass, which we'll call M. We'll assume that that mass is very small, and so that this length of this string, L, can be considered to be to this point mass. There is an angle here measured in this direction, and that angle is in theta, and that angle needs to be measured in radians. Now, it turns out that we will show that the simple harmonic oscillator with no damping here, this pendulum, is actually not a simple harmonic oscillator. It doesn't fit the mathematical equation of harmonic oscillator. But if you consider only small swings, that is, if you don't pull it up too far, like pull it up here and let it go, but just pull it a little ways, and if you use radians, then you can approximate it as a harmonic oscillator, and it can be used as a timing device. It was said that Galileo was watching a lamp swing in church, and he noticed that regardless of how wide the swing is, it took the same amount of time. Now, while this is probably doubtful that he actually did it this way, because we know that the lamp in the particular church was not installed till after his death, and if he used his pulse, as legend says, to time this, his pulse would have been running very slow. But it is true that Galileo did discover this fact, and from this fact came all of our ability to do modern timing, starting with the grandfather clock. So we're going to show you how this works. What's really amazing about this is that the period will only depend upon the acceleration of gravity, little g, and the length of this wire or string, and not upon the mass of the ball, nor how far you pull it back, provided the amount that you pull it back is still small enough for the approximation to work. So let me write down some of the results that you might want to know about this thing, and then I will prove these results. The first is that the angular frequency depends on g divided by the length of the string, that the time that it takes to make a swing is the square root of L divided by g, that the frequency is 1 over 2 pi times the square root of g over the length of the string, that the maximum here is not going to be x, but in fact it's going to be theta, and we'll generally call that theta naught or theta max. So instead of x, it's going to be theta. Our velocity here is going to depend on angular velocity, really. So you could in fact say that this is some omega. Generally this is not something that's given, and generally the acceleration max is not something that people will write down or expect you to know. What they will expect you to know is that the energy will depend on mg times the length of the string times 1 minus the cosine of theta max. Now, from that fact, you can then derive equations for the acceleration and the maximum velocity. I'll come back to those if I have time, but these are the important things: knowing omega, knowing the period, knowing the frequency, realizing there's some maximum angle, that's what we count displacement, and that the energy is equal to the dependent on mg times the length of the string, 1 minus the cosine of that maximum amplitude. Now, with that, let me prove these things. To start with, we're going to talk about rotational Newton too. So remember, I've got my mass here, and it's some angle theta, and it has some length. So I've got a ball, I have tension, I have weight, and there's this angle here, and I have an axis of rotation, and the sum of the torques about this point right here, call it point P, is equal to the moment of inertia about that point times the angular acceleration. Now, to calculate the torques, I need to figure out where the force is applied. Now, the tension has no torque because it lies along the moment arm. It has no perpendicular component. But this weight has a perpendicular component, and it depends on this part of the weight. So that would be weight times, I need the opposite, that's the sine of theta, times the moment arm. The moment arm is this distance L. And that's producing a torque trying to turn it this way, which is the opposite of an increasing angle. So it's a negative torque. That's equal to the moment of inertia times alpha. So solving for the angular acceleration, alpha, I get alpha is equal to minus mgl over IP times the sine of theta. Now, mass, g, length, and the moment of inertia, they all turn out to be constants. So there's no problem with this being a positive constant. But the angular acceleration has to be minus a constant times the angular position. And I don't have the angular position. This is not theta. And that's what it has to be. It has to be the angular acceleration equal minus omega squared times theta, the angular position. And this doesn't fit. So this is not, in general, a simple harmonic oscillatory motion. It's not an SHO. However, if we have small angle deflections, then sine theta is approximately theta in radians. One of those things that we know from trig. So that means that for small angles, alpha is approximately minus mgl over IP times theta. For a simple pendulum, IP is equal to the mass times r squared, but r squared in our case is L squared. So plugging that into our formula, alpha is approximately minus mgl over ml squared theta. Kill one of the L's and kill the m. Alpha is approximately minus g over L theta. And this is of the form alpha equal minus omega squared theta, where that's angular acceleration, angular position, and a constant. So we've now found omega squared for this problem. Thus, it is an SHO for small angles with omega squared equal to g over L. Therefore, omega is the square root of g over L. So we just found one of our results. We get the other results just by applying trigonometry. Omega t is 2 pi. Therefore, t is 2 pi over omega is 2 pi times the square root of L over g. So the only thing on planet Earth that you need to determine the period is the length of the string, because the acceleration of gravity is 9.8 meters per second squared. F is 1 over t. So that's 1 over 2 pi, the square root of g over L. What about how to write the angle? Theta is equal to theta max times the cosine of omega t plus phi. And there's my amplitude. Now notice this, it's important. It's the angle, theta, this, in radians, times the cosine of that gives us our position, which is an angle, in radians. Alright? These are the position of the bob. These is how it changes with time. They're not the same thing as these thetas. In terms of energy, we can find that as well. This bob has a length L. When it's down here, it had a length L. Its maximum was when we're at theta max. This distance here would be L cosine theta max. At that point, V would equal 0. So the energy would be K plus U, but this would be 0. So this would be mg times this distance h. But what is that distance? That's this distance L minus this distance L, which is L cosine theta. Factor out the L, you get 1 minus cosine theta max. There's all of the things that we said that we could find initially. You could solve for how fast it's going when it gets back down to here. It would obviously be going down here. It would have some angular speed times L would give you V. So you could in fact solve this by 1/2 I omega max squared and find the maximum angular speed. You could find omega x times L and find the maximum tangential speed. You also know that when it's down here, it's got a centripetal acceleration pulling upward, and that centripetal acceleration is v squared over r, which is L. So we know that A max is equal to V max squared over L. We can find all of those things from here and get formulas. I don't know any of those formulas off my head. I solve them when I need them. What's the most important thing about this oscillator? The most important thing is right here about the period. It doesn't depend on how much far you pull it back. It depends only upon the length. So by changing the length of the string, people can make timing devices with periods of any value they wanted. And hence they could make very accurate clocks. And this was a great advancement in travel, in communication, and in commerce. All right, we'll see you on another video.